Welcome! In this video I'll show you how to solve problem 6.7 as it appears in both the second and third edition of Griffiths Introduction to Quantum Mechanics. Now this problem is relatively long, so we will go step by step. It says, consider a particle of mass m that is free to move in a one-dimensional region of length L that closes on itself. For instance, a bead with frictionless which slides frictionlessly on a circular wire of circumference L. And this is the same situation that we saw in problem 2.43. So if you have been following my lectures for a while, for example, my lectures in Quantum Mechanics 1, we solved problem 2.43. Now what we want to do in part A is show that the stationary states can be written in that form right there. And that their allowed energies are that. Now, this part A, is going to be quite easy because we already solved problem 2.43. If you haven't, then you have to check out my other video. I will put the link in the description because that is where I explain the procedure. And as we will see, it is the same thing. So let me just go get my results. So what we found, so from problem 2.43, what we found there is that we had the two possibilities for our wave function. So psi n plus or minus x. This is old notation. We will have to adapt it. E plus minus I 2n pi x over a. And we found that the energy levels are 2n squared pi squared h bar squared over m a squared, with n being 0, 1, 2, 3, etc. Now, notice that, of course, there is degeneration here, but we will talk about it in a moment. Now, we are not dealing with this bead of circumference A anymore. Now, we have circumference L. So what we have to change is go from A to L. And that's it. There we go. So another thing that I guess you could change is that here, for example, we don't have e to the 2 pi I, we don't have the plus or minus, which we do have here. So the main difference is that instead of having n equals 0, 1, 2, 3, what you have to do is say, okay, psi n of x, this is 1 over square root of L, e to the I 2n pi x over L, but this time n is going to be 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. So instead of having the plus or minus in front, you basically put it into the value for n. And it of course doesn't affect here because n is squared, so plugging in plus 1 or minus 1 doesn't make a difference. That's why we have degeneracy. So that is how you do part A. It is really, really quick. Of course, how you find this wave function isn't all that simple, but again, that is what we found on another video. So if you want to see that, just click the link in the description down below. Part B. It says, now suppose we introduce the perturbation h prime is minus v0 e to the minus x squared over a squared, where a is some amount that is much smaller than L. Basically, this puts a little dimple in the potential at x equals 0, right? So we have some sort of drop, as though we bent the wire slightly to make a trap. Find the first order correction to the energy using the result that we found before. Now, what is that result? Let me just, as a quick refresher, write it down here. So how do we find the energies? The energy, so E plus or minus, the first correction, this is 1/2 of WAA plus WBB plus or minus square root of WAA minus WBB squared plus 4 modulus of WAB squared. Okay, so that is the result that we had, and they say to evaluate the integrals, exploit the fact that a is much smaller than 0 to extend the limits from plus or minus L over 2 to infinity. After all, h prime is essentially 0 outside of the range between minus a and a. Okay, so let's go for this. Now what we want to do is find first order correction. So we need WAA, WBB, and WAB. That's what we need. So let's go for WAA. Now, remember that WAA is our state A in the inner product with our perturbation. What is our state A? Well, considering two states, one positive and one negative, that's why I prefer this notation, because we do have two different states. One is the one with the positive, one is the one with the negative. If we write it like this, we are kind of hiding those two states into one. So this thing is simply, now this is an inner product. That means an integral, right? You cannot forget that it means that we have an integral here. So this is integral from minus L over 2 to L over 2, right? We are integrating over this circumference of circumference L. So of course we can go from L minus 2 to L minus 2 to make it symmetric. So we have psi A conjugate. Now, since psi A we can consider as the positive state here, and psi B will then be the negative one, then psi N conjugate will be e to the minus I 2 n pi x over L divided by the square root of L. Then we include the perturbation, which, as we can see up there, is minus V0 e to the minus x squared over a squared, and then finally we put psi A without any sort of change, right? And this divided by the square root of L. And there we have it. Now the exponents, these exponents cancel out, so we get minus V0 over L, integral from minus L over 2 to L over 2 of e to the minus x squared over a squared dx. Now this integral is very difficult to solve, and in fact we probably can't solve it explicitly. However, we know that L is so much smaller than a, then even if x ranges in a very, very large range, the change won't really be particularly large with respect to L. So L over 2 might as well be infinity, because a is so small that it's making this amount so small that it's going to take a long time to get to infinity. Of course, this is an approximation. This is not exact, but it's going to be good enough. Now this integral is a Gaussian integral. We have seen it many times, and again, it is a very, very important integral. So the solution to that integral is the square root of pi divided by what goes along the minus x squared, which in this case is 1 over a squared. So 1 over a squared, or basically it now multiplies by a squared. So this is minus v0a over L square root of pi. And there we go. That is WAA. Now WBB, this is going to be psi b h prime psi b. So this integral is same as before, minus L over 2 to L over 2, but now psi b is the negative exponent, so when we take the conjugate, we get a positive one. So I 2n pi x over L divided by the square root of L minus v0 e to the minus x squared over a squared e to the minus, now I 2n pi x over L divided by the square root of L. Now this integral is the same as before because the exponents cancel out. So just as before, we get minus v0a square root of pi over L, which means that WAA is the same as WBB in this case. Now we still need to find WAB. So WAB, whoops, what is that? AB. This is psi of A, H prime, psi of B. So let's plug it in. This is the integral from minus L over 2 to L over 2 of e to the psi A conjugate. So we get minus 2i n pi x over L. And then we have H prime, which is minus v0 e to the minus x squared a squared. And then we have e to the 2i n pi x over L dx. Minus, sorry, because this is psi b. So this time the exponents don't cancel out. So now we go minus v0, oh, and the square roots of L. So minus v0 over L, and then the integral, now we can change the limit of integration again. So L basically goes all the way to infinity, so like this, minus infinity to infinity. And then we have e to the minus x squared over a squared, and then plus 4i n pi x over L dx. So how do we solve this integral? Now, we have actually faced basically this exact integral in a previous problem quite some time ago. I think it was problem 2.40 something. I know I did it in my channel, but I'll show you how to solve it. So we have to turn this integral into a Gaussian integral. So basically, we need to complete the square, right? So we need to take this thing, so x squared over a squared plus 4i n pi x over L, and we need to complete the square. So how do we do it? Well, let's begin by isolating x squared. So we begin by just saying, all right, x squared, and we factor out 1 over a squared, which means that we need to multiply here by a squared. So a squared L. Okay, and with that, this is quite a bit simpler because now we already isolated x. So in order for us to complete the square, we need x plus now half of this. So this is 2i n pi a squared over L. This thing is squared, but we now need to compensate for the fact that we squared by subtracting this thing squared. But since it has an I, by squaring it, we get another minus, so this becomes positive. So we get, this thing squared. So we get 4n squared pi squared a to the 4th divided by L squared. Now let's make sure that we did this correctly. So I will now multiply through, and we should get exactly what we had before. So this is 1 over a squared, and then we have x squared plus 4i n pi x a squared over L minus 4n squared pi squared a to the 4th L squared plus this same thing. Okay, so this is correct. Okay, so it is very important that you do know how to complete the square. If this looks weird to you, then you should go back and learn very well how to do it, because this is something that you will need often. Okay, so now that we have this, we can simply plug it back into our integral. So we can now rewrite this integral as minus v0 over L, integral from minus infinity to infinity of e to the minus x squared over... Okay, let's begin with our notation immediately, actually. So minus 1 over a squared, and then we have x plus 2i n pi a squared over L squared. And then we have this other term, so let's just take it out. So we write it as minus 4n squared pi squared, and now a squared, because that a squared cancelled out the a to the 4th. And we can write this as e to this power, right? Because we can separate the exponents. And now the final step is that we say, all right, let's have a new variable, y, which is x plus 2i n pi a squared over L, because now dx is simply dy. So we can now rewrite this entire thing, right? Let's take everything that doesn't depend on x or y outside. So we get e to the minus 4n squared pi squared a squared L squared. And then we have the integral. The limits are unchanged. They still go all the way to infinity. And then we have, let's see, we have e to the minus y squared over a squared and dy. So this is simply minus V0. Wait, why did I... Yeah, I don't know why I put this thing there. I have no idea what it even is. Sorry. So minus V0 over L e to the minus 4n squared pi squared a squared divided by L squared. Yeah, and then we have square root of pi times a squared, which we can simply take out, so pi times a. And there we have it. This is WAB. So now we have everything we need to plug into this equation. So WAA and WBB we know are the same. It is simply this amount right there. So let's see. E plus minus 1. This is, now let's go here. So this is WAA plus WBB. So this is, we need to go further down there. 1/2 of minus 2 V0A. This is WAA plus WBB. And then we have to take plus or minus the square root of, and what is inside of the square root is WAA minus WBB. But they are the same, so that term cancels out. So instead we get 2 times, right, because the square root of 4 is 2, and we get the modulus of WAB. So we get plus or minus. So we get plus or minus 2 times the modulus of WAB, which is that thing right there. So we get, so the modulus means that this minus goes away. So we get V0 over L e to the minus 4n squared pi squared a squared divided by L squared, and then times square root of pi a. And there we have it. We can simplify a few more things. So we can, of course, divide by 2. We can also factor out, so e plus minus. We can factor out V0 a over L square root of pi. So we end up with plus or minus e to the minus 4n squared pi squared a squared L squared minus 1. Now let's check out part C, because we already found the energy that we were looking for. So part C says, what are the good linear combinations of psi n and psi minus n? We have been calling them psi a and psi b, but it's names, it doesn't really matter. Show that with these states you get the first order correction using this equation is basically first order perturbation theory. So let's find the good states. Now we know that the good states are basically those states. I'm thinking of notation, yeah, either n or minus n, right? So let's say plus or minus, actually that's going to be good notation. These are going to be some alpha, right? And then one of our states, which we can either call n or psi a, and then plus or minus some other constant, and then psi, well, in this case, it's either minus n or b, depending on the notation. So we basically want to find what this is. The problem is that we don't know either alpha or beta, at least for now, but we do know how to find them, right? Because as we also used in the previous video about the Griffiths problem, what we found while we were deriving the W matrix, right, in this degenerate case, is that beta is alpha times the first order correction minus WAA divided by WAB. And we already have all of those amounts. So this is alpha. And then we have E1, which is that thing right there, which isn't the prettiest in the world, but it's all right. So E1, this is V0A square root of pi over L, and then we have to multiply this by plus or minus e to the minus 4n squared pi squared a squared over l squared minus 1. And then we need to subtract WAA. But WAA is minus V0A, blah, blah, blah. So basically we add V0, so plus V0A square root of pi times L. So this cancels out with the minus 1. This and this cancel out. So this goes away, and we're left with only this part. So this product. And then we divide this by WAB, and WAB is that thing right there. So WAB is minus V0 over L, A square root of pi, and then the same exponent, right? So minus 4n squared pi squared a squared over L squared. And this means that basically everything cancels out except for the plus minus 1 and this minus 1. So we end up with minus or plus alpha. So this means that our good states are, let's say, psi plus. So this is alpha. So this is the case plus beta. So alpha psi of n, so let's stick to this notation, plus beta. But beta is, in the plus case, is minus alpha. So that means that we are minus alpha psi of minus n. Now what is this? So this is alpha factor of. Now let's plug in our psi of n. Let's go all the way up here. Psi of n is 1 over square root of L and the exponent. So this is 1 over square root of L e to the 2i n pi x over L minus, and then we have e to the minus 2i n pi x over L divided by the square root of L. Now this thing right there is a sine. Don't ever forget, sine of x is e to the ix minus e to the minus ix over 2i. So that means that this thing right there is 2i times the sine of what is inside. So we can write this as alpha over square root of L times 2i. And finally, we have here, this is actually without the parentheses, this is sine of 2n pi x over L. There we go. Now the question is, well, what is alpha? Well, since our states look like this, we can easily normalize this and write that alpha is simply 1 over the square root of 2. Because when we square this, so basically alpha squared plus alpha squared has to be equal to 1. So of course 2 times alpha squared has to be 1/2, which means that alpha has to be 1 over the square root of 2, right? Alpha is the normalization constant. So we can plug that in. So alpha is 1 over the square root of 2. So that means that we get 2 over the square root of 2, or simply we can write this as square root of 2 over L. There we go. And now we can go for psi minus of x, which is of course alpha factor of psi of n, and now plus psi minus n. So this will be alpha, which is of course 1 over square root of 2, 1 over square root of L, e to the 2i n pi x over L, plus e to the minus 2i n pi x over L. So now instead of having them subtracting like before, they are adding up. So let's put everything together. So square root of 2L, and this thing, right, we have to keep in mind that the cosine of x is e to the ix plus e to the minus ix divided by 2. So what we have here is twice the cosine of x. So this thing is twice cosine of 2n pi x over L. And of course, 2 divided by the square root of 2 is square root of 2. And there we have it. So this is the other solution. So basically our two good states are these. So now we wish to find the energy levels using first order perturbation theory, right? That is the last part in this problem. So what that means is that psi plus h prime psi plus, right? This will give us one of our energies, and when we do it with the negative one, we will get the other energy, and those will of course be the same because we are in a degenerate situation. Okay, so let's begin with this one. So this is the integral from minus infinity, or rather minus L over 2, all the way to L over 2, of this thing squared. Actually, no, so this is plus. So in the plus case, we are here. So we have square root of 2 over L, I sine of 2n pi x over L times our perturbation minus v0 e to the minus x squared over a squared. And is that it, or was there something else to it? Let me check. No, that was it. Okay. And then we have, okay, this has to have a minus in front, by the way, minus because it's conjugate. And finally, we have square root of 2li sine of 2n pi x over L. Whoops, sorry. And dx. So of course the minus signs cancel out. We pull the constants of integration to the front, so we get them squared. And we can also take minus v0. Okay, and we are left with integral from minus L over 2 to L over 2 of sine squared of 2n pi x over L and e to the minus x squared over a squared dx. Now this integral looks scary, but don't get too scared. So we know that sine squared of some, I don't know, z, I don't want to use x, this is 1 minus the cosine of 2z over 2, right? This comes, of course, because cosine squared plus sine squared is equal to 1, and cosine squared minus sine squared is equal to the cosine of 2 times what is inside, in this case z. So if we subtract these two, we get precisely that condition, okay? So that is another very important trigonometric identity that you should really know. It's very important. So this is equal to minus 2 over L v0. And now, let's see, so this is integral from minus L over 2 to L over 2, and now we have 1 minus this. So with the 1, we get minus x squared over a squared divided by 2. And then we have minus cosine of 2 times this, so 4 times n pi x over L, and e to the minus x squared a squared dx. So the first integral is very easy. If we, of course, approximate a to be much, much, much smaller than L, as we did before, it's in fact the same integral. This other integral could prove to be a little bit more difficult. So this first integral is easy to solve. We have actually solved it already. And by the way, let's not forget about this 1/2 factor there. And actually, we can just simplify this 1/2 with this 1. So the main point of interest here will be this integral, which I will call I2. So I2, right, I will exclude the minus sign. So I2 is basically integral from minus L over 2 to L over 2 of cosine 4n pi x over L e to the minus x squared over a squared dx. So here, what do we do? Well, first of all, let's start by changing our limits of integration. Just as we did before, we can approximate this to be basically infinite because a is so very small. Now, what else? How do we solve this? Well, this is not easy to solve like this. In fact, if we just leave it like cosine, there's not much we can do. But what we can do is write cosine in terms of exponentials. So cosine is 1/2 of e to the I alpha. I'm lazy, so alpha is simply 4n pi x divided by L. So, well, I guess then I should call it, instead, alpha should not include the x. So this is e to the I alpha x. And then we have plus e to the minus I alpha x, right? So 4n pi L, yes. And then we multiply by e to the minus x squared over a squared dx. Okay, so what now? Well, now we have these two integrals, which I will call I3 and I4, just to make sure that we go step by step and don't make any dumb mistakes. So I3 is the integral from minus infinity to infinity of e to the I alpha x times, so minus x squared a squared dx. So how do we solve this integral? Well, this is very similar to what we did before. Here we have to complete the square. So let's write the exponent as minus. So basically with this term first, so plus I alpha x. Now let's factor out everything that is connected to the x squared. So minus 1 over a squared, x squared minus I alpha x a squared. So now if we want to complete the square, we now need to, basically, I'm gonna do it step by step here. We now need to add and subtract this term divided by 2 squared. So basically, this term will give us a minus sign. So we will have to add and subtract it. And we get alpha squared, not x squared, of course, because that term comes from the square, which doesn't include the x, of course, a to the 4th, and this is divided by 4. And now we need to, of course, subtract this same amount so that we are not doing anything that is not allowed. So here I simply did a few more steps than I had before. Now this is minus 1a squared, and now we complete the square. So this is x minus I alpha a squared divided by 2 squared. And by doing this, we had to include this term right here, which is the square of this divided by 2, right? Basically the square of this part. So we only have plus alpha squared a to the 4th divided by 4 left, right? And we can now make sure that this is correct. So we just multiply through, right? We have this thing here, x squared minus 2 times this, alpha a squared x, and then this term squared, which is minus alpha squared a to the 4th over 4, which is the same as this. So yes, that is indeed correct. So basically, this is how we write this integral. So let's rewrite it. So this integral goes from minus infinity to infinity, e to the, and now let's see, x, well, actually we have to start with minus 1 over a squared, x minus I alpha a squared over 2 squared, and then e to the minus alpha squared a squared divided by 4, right? You have to consider that we need to multiply by that quantity, and dx. So this integral is, well, we simply have to use change of variables. Y is x minus I alpha a squared divided by 2, and dy is dx. So for that reason, our integral goes from minus infinity to infinity of e to the minus y squared over alpha squared, and this, let's write it as dy, and just put this exponent outside to emphasize that it doesn't depend on y. Okay, so this is square root of pi divided by 1 over a squared, but as before, we get the a up here. And I don't like the way that this looks, so I'm going to just correct it. So this is a square root of pi. And then e to the minus alpha squared. But what is alpha squared? Alpha squared is 16 n squared pi squared divided by L squared. And then we have a squared divided by 4. So the divided by 4 will turn this 16 into a 4. Okay, so this is I3. Now, what about I4? Well, in the case of I4, let's see. So I4, this is integral from minus infinity all the way to infinity of e to the minus x squared over a squared. And then we have, let's see, plus I alpha x. So here I haven't factored out the a squared yet, dx. But notice that this is basically the same as this, with the only difference of this sign in between. So here we will get, when we use this, when we complete the square, right, considering that we do the same procedure, except that with a plus, we'll get plus here, and plus here, and plus here, and plus here. So in the end, we get e to the minus 1 over a squared x plus I alpha a squared over 2, right? It's the only thing that changed. Everything else is the same. So this thing, right, it gives us the exact same result as before. A square root of pi e to the minus 4n squared pi squared a squared l squared, which is of course I4, which is exactly the same as I3. So let's plug them in here. So here we get twice our result, but we are dividing by 1/2. So this thing will be 1/2 times 2 times I3 basically. So we get simply I3, or a square root of pi e to the minus 4n squared pi squared a squared l squared. So now all of this we plug into this result here. So let's continue to the side. So we had minus v0 over L. We haven't solved this integral yet. So taking the limits to go to infinity, right? This is simply a Gaussian integral. And we know how to solve that. That is simply square root of pi divided by 1 over a squared, or basically a square root of pi. Now, this is a square root of pi minus our result, so minus a square root of pi e to the minus 4n squared pi squared a squared l squared. So we can now factor out this thing, so minus v0 over L, and then we have a square root of pi, and this is 1 minus e to the minus 4n squared pi squared a squared l squared. So there we have it. This is the energy corresponding to the plus case. Now we need to do the same, but for the other case, for this psi minus h prime psi minus. However, fortunately for us, everything that changes, the only thing that changes, right, because our new case, I'm going to show you explicitly why this happens so that there is no doubt whatsoever. So what we are going to do is, right, we have the integral from minus infinity to infinity, right, just plugging it in right away. And then we have, what was our result for psi minus? It is this thing, right? It is cosine. So we get this 2 over L. Cosine is real, so the conjugate is the same. So we get cosine squared of 2n pi x over L times minus v0 e to the minus x squared over a squared dx. But what do we do here? Well, we take the constants outside, so minus 2v0 over L, integral from minus infinity to infinity, and now we rewrite cosine squared as 1 plus cosine of 2 times what is inside, so we get 4 times n pi x over L, and then we have, of course, all of this multiplied by e, well, and this is divided by 2, e to the minus x squared a squared dx. So the 2's cancel out, right? And look at this result. This is the same that we had before, right? The only difference is that before we had a minus sign. Now we have a plus, but everything else is the same, right? We have this exponent here, which is the same as what we get there, and we have the cosine times the exponent, which is the same that we already solved. So we don't need to solve it again. We already know that this will be the same result. So let's see, where's our result? It is here. So this will be minus v0 over L a square root of pi, right? Because this thing right here will give us a square root of pi, and this thing will be now, instead of minus, it will be so 1 plus, and then we get a square root of pi times e to the minus 4n squared pi squared a squared L squared. And this is e minus. So basically, if you want to put everything together, e plus minus, this is minus v0 over L a square root of pi, and then we have 1 minus plus, because when it is e plus, we get a minus sign. When it is e minus, we get a plus sign. E to the minus 4n squared pi squared a squared divided by L squared. And now let's compare this with our previous result. So our previous result is right here. Now it might look a little different, but if we factor out a minus sign, right, all we need to do is factor out a minus sign. So we get minus v0 a over L square root of pi, and then we get 1 minus plus and the exponent. So you can see that we did it indeed arrive at the exact same result, and that makes sense, of course, because we were dealing with the good states, right? So we were able to use the first order perturbation theory. So that is part C. Now it was a little bit tedious, but it was simply a matter of solving integrals. Now part D says, find a Hermitian operator A that fits the requirement of the theorem and show that the simultaneous eigenstates of H0 and A are precisely the ones that we found in C. So this part is relatively quick, but it can be a little bit confusing. So let's think of some operator, and what we're going to do is take some operator A, and when it acts on some function, right, which in this case would be our wave function, but in general it's a function, what we will get is f of minus x, right? So this is basically what is called the parity operator. Now that will come into play once we start going into quantum field theory, right? It really starts coming on very, very, very often, a parity operator. But for now, this is basically just a little bit of a glimpse. Now, what are the eigenstates? Well, we can think what happens, for example, if you're dealing with an even function. So if we have a function f that is even, then applying operator f will give us what? Simply f of x, because we know that this is the same as f of minus x, because it is an even function, right? So what is the eigenvalue? It is 1, right? This is if f is the eigenfunction, right, the eigenvalue is 1. And if we're dealing with an odd function, then a applied to our function is minus 1 times our function, right? Because again, this is the same as f of minus x if our function is even. So that means that our eigenvalue is 1 if we are in an even case, or our eigenfunction is minus 1 if we're in an odd case. Now, we can take this, right, and think of our eigenvalues 1 and minus 1 as basically our alphas and betas. And if we go now take a look at the result that we found in C, where we found our good functions right here, right? Well, what did we get? We got eigenvalue minus 1 or eigenvalue 1, right? So basically, what we see here is that what we got are the even and the odd results, right? So basically, the parity operator would indeed behave in the way that this particular wave function behaves. So there we go. That part is just more analytical, but there we go. That is D. So the parity operator behaves the way that these wave functions behave. So I hope this was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.